In optics, there are two kinds of magnification: linear magnification and angular magnification. What's the difference? The linear magnification is the ratio of the size of the image to the size of the object. Let's say, for example, that you're looking at the moon with a refracting telescope. The objective lens creates a real image, and you look at that real image through a magnifying glass called the eyepiece. Depending on the size of the telescope you're using, the image you are looking at is perhaps a few centimeters tall. That is clearly a lot smaller than the actual moon, which is about 3,500 kilometers or 2,200 miles in diameter. The linear magnification is very small, the image being literally, and I'm using the word literally, a few billionths the size of the actual moon. But viewed through the eyepiece, the image of the moon looks huge. In other words, the angular magnification is big. For a typical amateur telescope, the angular magnification might be anywhere from 20 to 200. Why? Because the prime focus image is only a few inches away from you, not 380,000 kilometers like the actual moon. And you're looking at that image with a magnifying glass. Again, the eyepiece. So we define the angular magnification of a telescope as the ratio of the apparent angle formed by the telescope image to the actual angle subtended by the object without the telescope. And it turns out that that ratio is equal to the ratio of the focal length of the telescope to the focal length of the eyepiece. For a simple refractor, the focal length of the telescope is the focal length of the objective lens, since that's the only optical part other than the eyepiece. As an actual example, here's a small refracting telescope. Its focal length is 700 millimeters. I know this because the manufacturer labeled it right here, and I'm assuming they didn't screw that up. Right now I don't have an eyepiece in place. Instead, I've put a piece of cellophane tape, the translucent kind, to act as a projection screen. Normally that's not there. I've aimed the telescope at some distant flowers, and here, on the tape, you can see the prime focus image created by the objective lens. You've probably noticed that the image is upside down. An important point is that the prime focus image is there, even if I remove the tape. If I put in an eyepiece and adjust its position so it's one eyepiece focal length away from the prime focus image, I'll get a new magnified image of the prime focus image. I have two eyepieces, 20 mm and 10 mm focal length. Using the 20 mm eyepiece, the angular magnification is 35. Inserting this eyepiece and adjusting it to be the right distance from the prime focus image, here's the view of those faraway flowers. The other eyepiece has a focal length of 10 millimeters, which yields an angular magnification of 70. Here's the view using that one. A shorter focal length eyepiece yields a higher magnification. You know that I'm a trustworthy guy, so I'm sure you believe the equation I showed you earlier, but let's do a mathematical proof anyway. To understand the following, you'll need to already understand ray tracing diagrams and how refracting telescopes work. Imagine you aim a refractor at the moon, so the axis of the telescope is aimed at one edge or limb of the moon. Rays from this point are drawn in black in this ray tracing diagram. Rays from the opposite limb of the moon are drawn in red, and these 2 points in the sky are separated by an angle theta in, called the angular diameter. For Earth's moon, viewed from Earth's surface, theta in is about half a degree. In the diagram, the black rays are on the axis of the telescope, so they will converge on the axis. The red rays, however, are off-axis, and will converge off-axis. The prime focus image is a distance equal to the focal length of the objective lens away from the objective lens, by definition of focal length. The moon is so far away, the rays entering the telescope are plane waves. Recall the three principal or easy rays we draw when tracing light rays: the parallel focus ray, the focus parallel ray, and the central ray. Feel free to hit pause at any time here and follow all the rays in the diagram and make sure you understand how they were drawn. They are all principal rays, except for the rays I've labeled 1 and 3. They were drawn simply to the place where ray 2 crosses the focal plane, the focal length of the lens away from the objective. This is the size of the prime focus image. You could put a piece of film here and record a picture of the moon, and it's clearly very small compared to the actual moon. In other words, the linear magnification is way small, like I said earlier. perhaps a few billionths. But what we're concerned with here is how big the image looks, its angular diameter, theta out, compared to the angular diameter of the moon seen without the telescope, theta in. The prime focus image becomes the object for the second lens, the eyepiece. We've placed the eyepiece at a distance from the prime focus image equal to its focal length, which is much shorter than the focal length of the objective lens. Here are the principal rays. Now might be a good time to pause the video to study this carefully. Because they are coming from one focal length away from the lens, they will emerge from the lens parallel. Note the yellow and green triangles. They share a common side, the prime focus image, marked with a dotted line. Call the length of that line x. For small angles measured in radians, the length of this line equals the focal length of the objective times theta in, and it also equals the focal length of the eyepiece times theta out. Set these two expressions equal to each other and rearrange, and you get theta out over theta in, that is the ratio of the angles, is equal to f objective over f eyepiece, the ratio of the focal lengths of the objective and the eyepiece. We call this ratio the angular magnification because it looks, when you look through the eyepiece, as if the opposite sides of the moon are separated by a larger angle than they are without the telescope. That's why the view through a telescope is as if you were closer to the moon. If the angular magnification is 70, for example, like it was with those flowers, the view looks like it would if you were 70 times closer to the flowers or to the moon than you really are. You can easily change the magnification by swapping out eyepieces with different focal lengths, as we did looking at the flowers.